You? Somebody did it. Okay, I mean, if you're clear, you got it. So we'll move on. All right. I didn't give you any problems with the lost tab. There's none in this book, but you should be aware that you have to understand complex primitivity. Later on, it will become useful. So we did skin depth, and now we're doing power flow. So I try to kind of relate this stuff to circuits. You know, when you talk about circuits, you first learned about voltage, current, and resistance, right? There were the three fundamental things when you had, I mean, you learned about capacitors, inductors, but that's really later. And you learned that power is really V times I in the instantaneous sense. Well, you have learned about the electric field and the magnetic field. Power is really going to be the product of the magnetic field times the electric field times the magnetic field, much the same as voltage times current gave you power with circuits. Did you follow me on this? At least the thought process. So when we talk about an electromagnetic field propagating, when we have an E field, I think we might have this marker somewhere. When you have an E field as such, and you have an H field, and this is for propagating electromagnetic field. They have to be orthogonal if we're talking about an electromagnetic field that's propagating. And there's a direction of propagation as such. Well, there's two forms of power. One is the instantaneous. Remember, the instantaneous form of power when you had a circuit was V, the voltage across an element, V of t, times the current through the element, at that time, I of t. You all remember that? So when you talk about the instantaneous form of power, that's equal to simply E of t crossed into H of t. That would be the instantaneous power. It'll go to 0, and it will go to some max. Do you all follow me? Now remember, power, when you take a look at power flowing through a resistor, if you have an AC or a time varying field, you get a peak value, then it goes to 0 and another peak value. Do you all follow me on that? There's an average value we also talk about. This would be the instantaneous power flow, and the units are going to be watts per meter squared, and this is power flow, by the way. Then there's the average power flow. And it's really a power density. The average power flowing is going to be 1/2 the real part of E crossed into H conjugate. Now, that's the one that's very similar to, remember how you got the average power dissipated in an actual resistor, really in any element, but in a resistor especially. If you had a voltage across the resistance and a current through it, and you were in the phasor domain, the actual average power dissipated was equal to 1/2 the real part of V times I conjugated. Do y'all remember that? Remember that, class? So this is what we usually use. The units are watts per meter squared. And now I'm just going to develop this for the standard way Wentworth goes, that he does business. He assumes that we have an electromagnetic field propagating in the z direction, and I'll draw it here. So in Wentworth's book, what he usually does is he assumes that you have an electromagnetic field, and this is going to be the x direction, this is going to be the z direction. And it's given by some E naught e to the minus, we can go lossless here, minus, no, actually, let's not go lossless. Let's assume it's lossless, possibly lossless. E to the minus gamma z in the AX direction. Y'all follow me on that? That's just the standard form here. Gamma is equal to alpha plus j beta. And then the result is, the H field for this would be given as simply 1 over the magnitude of eta here. And eta, of course, is equal to the square root of j omega mu over sigma plus j omega epsilon. And I didn't put it down, but gamma is equal to the square root of j omega mu times sigma plus j omega epsilon. So it's 1 over eta, and then it's going to be equal to the unit vector in the direction of propagation crossed in to the E field in phasor domain. And this will get you 1 over the magnitude of eta here. Then it's going to be times E naught. And I can go through the crossing if you want me to, but this is what it's going to come down to. Then it's going to be E to the minus gamma z. And because eta down here has a phase angle, when phase angle comes upstairs, it's negative, so it's going to be E to the minus j, and now it's the phase angle associated with the intrinsic impedance, and it would be in the AY direction. If this is propagating in the X direction, AP is in the Z direction. When I have AP or AZ cross AX, you get AY. Do y'all follow me on this, class? Now I'm going to expand this a little for both of them. That means if I take a look at the actual E field and H field, the E field itself, for this simple waveform, we'll have some magnitude E naught. This is going to be a wave propagating in the positive Z direction. E to the minus alpha Z, E to the minus J, beta Z as such in the AX direction. And the H field, these are both phases, would be E naught over the magnitude of eta, E to the minus alpha Z, E to the minus J beta Z, but it will also have that E to the minus J angle associated with eta here in the AY direction. I have to make sure that you understand what I'm talking about with the angle of eta. You see how generally this could be a complex quantity, not a strict real, if you had a value of sigma that wasn't 0. So this has a magnitude of eta, and it's at some E to the J angle associated with it, whatever that may be. It has a real and imaginary part generally. Y'all follow me on this, class? All right, now when we get the power flow, average power flow, we take 1/2 the real part of E, and I'm using this form right here, cross H conjugate. The real part of E, so I just rewrite that. In the AX direction, then I cross that with H conjugate. So what would this be conjugated? Just tell me. Do y'all know what conjugation is? Let's make sure you do. Suppose I had A is equal to 10 at an angle of 30 degrees. What's A conjugated? Anyone?
10 is negative 30.
10 at an angle of minus 30 degrees, right? You simply flip the angle. If it's positive, it becomes negative. Y'all follow me on that? That's conjugation. How many remember conjugation? It's something, it should be ingrained in you from your math courses because it's used so often in engineering. And likewise, if I said B was equal to 2 plus J5, what would B conjugated be?
2 minus J5.
That's right, 2 minus J5. You simply flip the sign on the J term. Okay? So it's cross, this is a cross operator, circle that, into the conjugate. Well, E naught over magnitude of eta doesn't change. The E to the minus alpha Z is strict real. Now that's imaginary, right? E to the minus J, beta Z, so when we conjugate it, we get rid of that negative sign. You all see this, everyone? So then I have E to the plus J beta Z. And this one too, there's a minus here for that angle. E to the minus J times the amount becomes E to the plus J, angle associated with eta, and it's AY. I'll let you take a look at that for a minute. Everybody okay with what I've done? And the only thing I'm doing is literally just taking these two forms of E and H and I'm plugging them into that definition of the average power flow. Follow me? Now, I turn the crank on this, and I want the real part of all this. So first of all, I have 1/2 out in front. Now I want the real part. Now, E naught is a strict real number. It's like 5, 10, something like that. I got E naught times E naught, that's strict real, that's E naught squared. I have eta, magnitude of eta, that's strict real, right? So I'll put those out first. 1/2 magnitude of E naught squared over magnitude of eta. Now, the next thing I take a look at is I have e to the minus alpha z. That's like e to the minus 3z. It's always real. There's no possibility of an imaginary number there. I have e to the minus alpha z. That means it comes out as e to the minus 2 alpha z. Next thing I have is e to the minus j beta z. It's times e to the plus j beta z. What is that?
0.
It's actually e to the 0, which is 1. Y'all follow me on that, class? You simply add exponents. So that, the imaginary stuff here and here cancels. Then I'm left with this term. So we'll deal with that in a second. But then we have ax cross ay is, class? It's az. And then we want the real part of e to the j theta, right, theta? So do you remember the identity we used for that? E to the j theta is what? Cosine of theta, right, plus j sine theta. You all remember that? And the real part would be the cosine. What's the name of that identity? Euler's, right? Don't forget that. Like the old Houston Oilers, only spelled with E-U-L-E-R-S, not O-I. It's Euler's identity. And the real part of that would just be cosine of the angle theta n. And this is important to understand. This is watts per meter squared. So this is power flow generally for a plane wave, assuming it's propagating in one direction. And for this, in this case, we're assuming the E field's in the X and the H field's in the Y direction, but it doesn't matter. That power flow has to do with any type of E field that's propagating in one direction, really it's propagating in either Z, X, or Y. You could replace Z there with X or Y if it's propagating in the other two. And it's also assuming a plane wave, right? That we're a long way from the source, so there's not that 1 over R fall. It's a plane wave. Yeah.
Could you explain the units a little bit more? Why it's
The what?
Could you explain the units a little bit more? Why
Sure.
it's watts per meter squared?
All right, if you take a look at this, here, E field is volts per meter, right? H field is amps per meter. Volt amps is watts per meter, meter squared. Watts per meter squared, and that's power flow. That's flowing, it's not being dissipated. Y'all follow me? There is going to be power dissipation, we'll talk about it a bit. So that's the average power flow right here, and this is the one that's generally true. Now, when we talk about power flow, I'm trying to do this the way he does it. Yeah.
On the average power equation, for the H field, how does the E to the imaginary beta Z become positive? Same thing with the amp.
When we conjugate, if you look here, remember it's E cross H conjugate. When you conjugate it, that stays the same. That's strict real. This becomes positive J beta, right? And this becomes positive. So positive, positive. And then when you multiply them, the effects of that, or he gets rid of the E to the J beta term completely. All right. So that's it. And if you take a look at this, we'll look at some extremes. We're going to take average power flow in a good conductor, and then a perfect dielectric. By the way, has anybody looked at the videos of this course? He's gonna put it up. Anybody? No, I have. I mean, just briefly, thank you for doing it. It's made available for your benefit, by the way. And you have a group me page, right? How many of you join that? All right, I hope, especially in the future, you'll interact and stuff like this. It'll help, usually helps you. I sure hope it does. So we're gonna take a look at that power equation in two extreme domains. First, we're gonna take a look at what happens to that power flow in a very good conductor. So when I talk about a good conductor, what does that mean to you?
Lossless.
No, it's not lossless, it's very lossy.
Sigma is much larger.
That's right. For a good conductor, we assume sigma is much, much greater than omega epsilon, right? And this is all about this equation. Curl of H is equal to J, which is sigma E, plus J omega epsilon E. This is in the phasor domain. So if this term is much, much larger than this term, or if sigma is much, much larger than omega epsilon, it's a good conductor. It means there's going to be a large current density that's real relative to displacement current density. So this is true. Now we take a look at some of the facts. That means, first of all, in a good conductor, we have eta is equal to the square root of J omega mu over, generally it's sigma plus J omega epsilon, right? But because of this assumption, what happens?
J omega and J goes.
Just erase J omega epsilon, right? So I'm down to there. Now, that means I have eta is really equal to the square root of omega mu over sigma, but what is J really? J is equal to e to the J pi over 2 or 90 degrees, right? Y'all with me on this, everybody? So if I take the square root of that, it's e to the J pi over 4, right? Or 45 degrees. All right? So now we got a complex impedance. It's got a magnitude, but its angle is 45 degrees. It's no longer 0. So I have a real and an imaginary part to it. That's the first. Second thing is, what happens to gamma? This is something I'm trying to stress. I know gamma is equal to alpha plus J beta is equal to the square root of J omega mu times sigma plus J omega epsilon. But if sigma is much, much greater than omega epsilon, I can erase it, can't I? So I'm gonna. Now I have this. And what does this become? This one I break down a little differently. How many remember me doing this at least, if you don't remember exactly what comes out of it? Sure, this one becomes, it's equal to simply the square, it's really, J is equal to e to, J right here is 1 at an angle of 90 degrees, the square root is 1 at an angle of 45, or it's 1/2 plus J 1/2. And this will come down to simply be equal to square root of pi f mu sigma times 1 plus J. And this means that alpha is equal to beta in a good conductor is equal to the square root of pi f mu sigma, right? Remember this? Now if you've done your homework, I hope you have. Do you remember this term? What is that called? And I don't mean something to do with a lost end.
Skin depth.
It's skin depth, right? What is skin depth? Well, skin depth fundamentally is just 1 over alpha, right? And it's equal to 1 over the square root of pi f mu sigma. Remember that. Those are things that should be almost automatic. You shouldn't even have to think about it. It'll be so, good conductor, this is the way it is. I got it. And if you keep up with the homework, you probably will get to that point without much trouble. So now, I've got that, and now I'm going to get average power flow in a good conductor. And again, this is all for a good conductor. So that means average power flow is equal to 1/2, take a look at this, times E naught squared over the magnitude of eta. Well, eta is just omega over square root of mu, omega mu over square root of sigma, or square root of that actually, square root of omega mu over sigma. I'm gonna leave it like that. Then it's gonna be e to the minus alpha, 2 alpha, so it's e to the minus 2 times square root of pi f mu sigma times z. And I on purpose put in the alpha, just so you can see it all at one time, right? Because that's alpha. Then it's gonna be the cosine of what angle? Class? Cosine of the angle associated with eta, and what's that angle?
Pi over 4.
Right, or 45 degrees, right? I'm gonna put it here, cosine, I'll leave it as 45 degrees, because sometimes it makes a little more sense to you. In the AZ direction, it's watts per meter squared. I'm gonna simplify it yet again. That means average power flow in a good conductor, the 1/2 stays, right? Now, I'll leave E naught squared by itself. I can flip this if I want, but there's no real need to do that. I can say this is really the square root of sigma over omega mu times e to the minus 2 square root of pi f mu sigma z. And what is cosine of 45 degrees mathematically? 1 over the square root of 2, right, that's a good way to write it. So I can simply take this thing and simply put this times 1 over the square root of 2 in the AZ direction. And that's power flow in a good conductor if it's flowing in the Z direction, right? Now that's it. But you can plainly see that if you have power flow in a good conductor, this rapidly attenuates. It just basically goes to 0. After 5 skin depths down, it is about 0. You all follow me? That means when this is e to the minus 2 times 5, or e to the minus 10, and that's about 0. It's not exactly 0, but it's getting very close. It's so small compared to the initial power flow that was entering the media that's very conductive. You all follow me on this class? All right, so that's power flow in a good conductor. While I'm at it, I asked this before, but do you remember what the phase velocity would be in a good conductor? Anyone? Well, what is fundamentally phase velocity? Just tell me that. Remember? It's very fundamental. I'm trying to encourage you to. It should be there. It's always omega over beta, right? Omega over beta, or 2 pi f over beta, which is square root of pi f mu sigma. All right, now I'm going to leave it like that for now, but y'all see how you can combine the f? This is really what? Square root squared, you might say. So if I do this, I'm going to get a square root of f on top. I'm going to get a square root of pi. I'll leave 2 alone, and then I'm going to have square root of mu and sigma on the bottom. But that's phase velocity, right? What's wavelength, fundamentally? Say again?
2 pi over beta.
That's right, 2 pi over beta. So wavelength would be 2 pi over beta. Now you can see, I can just stick in the beta or the alpha there, right, because they're the same. And you got wavelength. Y'all follow me, class? Just showing you. All right, that's in a good conductor. Now, what about a lossless medium? So that's good conductor, and if we have a lossless media, doesn't necessarily have to be free space. It could have a value of epsilon relative that's relatively large, or a value of mu relative that's large. But if it's a lossless media, what does it mean? Sigma is 0, right? There's no conduction current, no losses. And you could say one other thing. You could say epsilon double prime is also 0. That's not what we're spoke, but if it's lossless, epsilon double prime is also 0. So if those two things are true, then what you can find out is that that equation that I had over there, when I look at the average power flow, that's equal to 1/2. Then it's going to be the real part of E cross H conjugated, but because it's lossless, there is no alpha either, is there? If it's lossless, alpha is 0, correct, class? The angle associated with eta, let me just tell you what I'm talking about. If it's lossless, then eta itself is equal to the square root of j omega mu over sigma plus j omega epsilon. But because sigma is 0, it's over j omega epsilon. So it's really square root of mu over epsilon. So the angle here is just 0, right? It's strict real. Do you all agree with that? It's e to the 0. And then when we talk about the propagation constant, which is alpha plus j beta, it's simply going to be j beta. Alpha will be 0, and that will be equal to simply j times omega square root of mu epsilon. Right? And you can see that from over here. Did I erase that? Yes. No, I didn't. If you had done this plus j omega epsilon, if you got rid of the sigma in this case, you got j omega squared, square root of, you bring out that j omega and you have square root of mu epsilon. That's what that is. So this means that beta itself is just equal to omega square root of mu epsilon if it's lossless. Do y'all follow me? And again, I'm just pointing out facts. Now, for this thing, I can rewrite the E and H field, but it'll come down to this. You can take the general form I had, and it'll simply be 1/2 magnitude of E naught squared over magnitude of eta, and then it's going to be simply in the A's direction. There is no cosine term. There is no e to the minus alpha z, and there is no e to the minus j beta z or anything like that. All right, that's strict rule. One thing you notice is it's constant. Doesn't vary spatially at all. You all see that? And that means the power density, average power density for a propagating wave, plane wave in a lossless media is constant. It doesn't change. It's just like average power. If you have if you're talking about AC power, and you talk about how it's delivered, now I'm not going to be able to fit this exactly the way I want, but I was trying to draw a parallel between no line losses and the actual power flow down a transmission line. Have you had Gross yet? Did you have him for power? Now, I don't know if he does this, but when you do transmission lines, do you do lossy and lossless transmission line power flow? If it's lossless, then the power flowing down the line, if you just look at a three-phase system, is always the same. If it's lossy, then some power is going to be dissipated, but I have no idea if he does that kind of stuff in power at that level, because you're still junior level when you take it, right? You know, it's not 400 level or 4,000 level. So that's average power flow. And one other thing here. Beta is given by that, right? So what is the phase velocity? It's always what? Omega over beta, right? Now take a look at this. If that's beta, what is this? Well, it's omega over omega square root of mu epsilon. It's really 1 over the square root of mu epsilon, which is really the speed of light divided by the square root of mu relative epsilon relative. And what's wavelength? 2 pi over beta, right? And beta itself is just omega square root of mu epsilon. So that's wavelength too. And if you want to, you could say that omega right here is 2 pi f, and you can get rid of the 2 pi's on the top, and you have f, right? And this really would boil down to the phase velocity over the frequency, and that's true. So this would be really c over the square root of mu relative epsilon relative divided by f. And in a vacuum or in free space or in air, the wavelength is just c over f. And I think some of you probably remember that from physics. All right, so that's power flow in a good conductor and in a perfect dielectric, the two extremes. I'll talk a little bit about polarization. And I'll tell you first, ahead of time, why polarization is so important. And what I mean by it. Polarization has a lot of different meanings, depending if you're talking about chemistry, or if it's political science, or just about any field that can mean different things. This is the physics definition of polarization for a propagating wave. I'm saving doing problems to the end. So, when you talk about polarization, what's meant by that is the orientation of the electric field as it moves through space. So I need to talk about this, try to make sense with you. If I have an electric field and it's polarized in a vertical direction called the x direction, but it's propagating that way. Electric field will have this orientation. It will have a peak value that's positive if you took a snapshot in time. Then it would go through a negative, there would be a negative value, positive, and so forth. But it's always either oriented this way or this way. You all follow me? And it'll just have a sinusoidal variation to that wall. That's called linear polarization. If the electric field is only polarized on one line, you might say. That's linear polarization for a propagating wave. Now, if I have two electric fields, just follow me, same exact frequency, only one is polarized this way, in the horizontal direction, one in the vertical. Well, if they're both in phase, then you would still have linear polarization, only would be at an angle. You all follow me? Now, if you have these two, but they're actually skewed by 90 degrees. In other words, where one's a peak, another is a minimum. You all follow me? Then you would have, if they were the same magnitudes in the horizontal vertical, then what would happen is if you could just be at one point in space and let time proceed, then you would have something where the magnitude of the electric field would always be the same, but it would turn either to the, it's called right-hand polarization. If you have a right hand and you put your thumb in the direction of propagation and your finger in the direction of the E field, if the E field rotates like you're opening a door with your right hand, that's called right-hand circular polarization. If you have a left hand, you put it in there in the direction of propagation, and if the electric field rotated in time as you would open a door with your left hand, the opposite way, of course, then that's left-hand circular polarization. Do y'all follow me? Now, it doesn't have to be just circular. You could also have elliptical. If the E field, say, it was twice the E field in this direction, instead of a circle that would be traced out by the tip of the electric field, now you would get an ellipse. Do y'all follow me? And you can have an ellipse that has a given tilt. Doesn't have to be just this way. It could be this way, or it could be this way. Do y'all follow me? So that's what they mean when we talk about polarization of the electric field. It's usually termed either linear, circular, or elliptical. And here's why it's important before we get into the mathematics, which are trivial. And I teach radar, and I do a lot of work with, or I'm involved with radar work and other types of remote sensing things. So when I have a radar unit and I send out a right circularly polarized wave and it hits something that's a conducting body, like an aircraft, then it returns a left-hand circularly polarized wave. Y'all follow me on that? Now, there are polarization filters. I can filter out anything but left-hand polarization. So now, when the signal's coming back, anything with right-hand polarization, even if it's at the same frequency as I'm transmitting, I ignore it because that can't be a reflected signal from my transmitter. But everything that's left-hand circular polarization, that frequency I'm transmitting, I pay attention to, and I go ahead and I analyze it to see how far away the target was, what the time delay was, and stuff like that. And that's how it's used in radar and why it's so important. Now, in weather radar especially, this is meteorology, they like to differentiate not just the intensity of the backscatter, but they like to get the velocity field. So it's my understanding, by the way, I've never worked on a weather radar per se. I'm just involved with some stuff around I have to be aware of. So when you have rain, it's typically a teardrop shape, if you know what I mean. It's longer one way than the other. It means if I have an electric field oriented along that raindrop's alignment, it'll have a maximum reflection back to me when it's along the long axis. If the actual raindrop was, say, this direction, my electric field was this way, it would have a minimum amount of reflection. Do y'all follow me? So when rain's falling, it'll fall along the velocity field of the wind. So it could be falling like this. Some of you know what I'm talking about. You know how you get hard rains with high winds, and the rain's coming in sideways at you. That means the teardrop shape is this way. So they'll have radars that will be elliptically polarized, and they can change the orientation of that ellipse. And when they're getting a maximum return from that cloud structure, they know that's how the raindrops are oriented. And they can more or less diagnose the velocity field. They can also get something called the Doppler shift involved. Some of you have heard of Doppler weather radar. Just by knowing something about the shape and the returns of these raindrops, they can give a whole, well, it doesn't have to be raindrops, there's a thing called hail, and we're familiar with that, that's just hard, solid water falling. And then there's something called graupel, that is slush. And they all have a slightly different characteristics of their backscatter and things like this. But by just knowing polarization, how to do polarized waves, and knowing something about Doppler shift, they can diagnose pretty much when there's really severe weather, when there's a tornado that's actually there from a hook echo. And they get a whole lot of information from radar units that are hundreds of miles away, which is kind of interesting because a person on the ground, even a mile away, would have a hard time looking and extracting that kind of information. So that's the reason that's important. Back to this polarization. So if you talk about plane wave propagation, and now I'm going to assume that it's propagating in the z direction and z is out of the board. I'm going to do it this way. I'll call this x, call this, actually I better not. I'll call this x and call this y. And then z is out of the board, so now I'm taking a look at an electric field. And let's actually call this the EX vector and call this EY. So if I do this, this is at z equals 0. I'm going to say, I know the electric field is going to be made up of an x component, EX, and EX I'll just put as some E naught right here, and it's going to be cosine of omega t, AX plus some E naught right here times cosine of omega t, AY. All right. And I'll just show you how you actually figure this out. Anytime you have polarization, this is how it's done. There's a mathematical statement for the electric field in the time domain or the phasor domain. If you got one, you got the other. So now, the only thing you do is increment the argument by about 45 degrees and see how the hands move, if you will. All right, you want to see what the actual value, the electric field projections will be here, and how the tip of that wave is moving. If you take a look at this, when omega t is 0, that would be the starting point. Cosine of 0 is 1. So I have E naught AX and E naught AY. I would have something like, we're going to have to do the extremes. This would be E naught, this would be E naught. That point is right here. That would be point 1. Do y'all follow me? I'm just incrementing omega t. It's an angle, isn't it, class? Omega t has got to be an angular target. Now let omega t be equal to 45 degrees, or pi over 4. What's the cosine of 45? 1 over square root of 2. It's less, right? But both here and here, this would be E naught over square root of 2. This would be E naught over square root of 2. So it basically would be on this line, it would be here, right? Now, let omega t be 90 degrees. What's the cosine of 90? 0, right? Now it's going through here. I've only done 3 points here, but you can see what I'm going to get is a straight line that goes like this. You all see that? It's just the tip of that electric field is tracing out a straight line. That's linear polarization. in Wentworth's book, he'll talk about, he wants to know the tilt angle here. And it doesn't matter where it's from, he'll call this the tilt angle. I don't care about that, and neither does anybody else. You can see it's 45 degrees just by plotting a few points, right? So this is simple linear polarization with a tilt angle of 45 degrees. If I wanted linear polarization with a tilt angle at 90, I just get rid of the AX component. Make E naught there 0. So I only have a Y component. If I only want it in the X direction, or I want the tilt angle to be 0, I get rid of the EY component. Y'all following that? Nobody cares about the tilt angle until you do weather radar and stuff like this, and then it becomes important, but not in a way that it's mathematically you have to do some clever thing. It's basically to get the maximum return at a certain tilt angle tells me the orientation of really the rain field. All right, so now the next case, I'm going to use this, but now I'm going to say instead of this, I'm going to put a 90-degree shift here. It's going to be E naught cosine of omega t plus pi over 2. Y'all follow me? Same exact equation. This will be EX, and this is EY. And I start plotting. So I always start at omega t is 0. When omega t is 0, I have the X component is E naught, so it's out here. Y'all follow me? That's E naught. This is the first point. Now what's the Y component at? Class? Well, if omega t is 0, I still have cosine of 90. What's cosine of 90? It's 0, right? Y'all follow me? It's 0. As a matter of fact, this is my first point. So the electric field, the hand on the electric field clock would be there. That would be point 1. Y'all follow me? That's at omega t is 0. Now, turn the dial. When omega t is 90 degrees, or was 45 degrees, cosine of 45 is 1 over square root 2. So I know on the x-axis here, it's going to be a little less. It's going to be E naught over square root 2. Correct, class? Now come over here. What's the cosine of what? 90 and 45 is 135. Remember how a cosine waveform looks? If you take a look at a cosine waveform, it does this, right? So this would be at 90 degrees, right? This would be a cosine. This is at 0. And at what? 135, or it's actually right here, it would be minus E naught over square root 2, wouldn't it? Right? It's same, it has a magnitude of E naught over square root 2, but it's negative, right? It means it's down here. So this would be E naught over the square root of 2, but it's negative. And then you can see what happens is, here's my hand of the clock. That's the first hand. The second hand of the clock is down here. And you'll notice the magnitudes are the same. If you square the x component, square the y component, take the square root, they both equal E naught. I mean, this is minus E naught over square root 2, this is square root 2. So square both components, you get E naught after half, add them up, you get E naught squared, right? Square root of that is just E naught. Do y'all follow me? As a matter of fact, what this is a clock hand turning in this direction, right? Now, if it's propagating out of the board, what kind of polarization is that? Position 1 is there, position 2 is here. You can see position 3 be there. As time progresses, it's doing this. What kind is it, left or right? You got a right hand, all right? Put your right hand in. Is it going this way? No. Take your left hand. Put your left hand thumb in the direction of propagation. Is it going that way? Yes, it's left hand polarization. Do y'all follow me on that, class? So, next, what do you think happens when I do this? Or I can do something over here. There's so many ways to do this. What do you think happens when I do that? Take a guess.
It's right hand polarization.
Yeah, what are you going to do? You want to take a look at one thing. At omega t equals 0, right? That's still 1, right? What's this? That's still 0, right? Cosine of minus 90 degrees is 0. Now go omega t, let it increment a little. Let omega t become 45 degrees. That's 1 over square root of 2, right? When this is 45 degrees, what happens? Cosine's an even function, right? It's positive, right? This is going to be positive E naught over square root of 2. Do you all follow me in that class? And now you got right-hand circular polarization. Do you all follow me? But these are just things. The only thing you need to do, if you got a mathematical equation, just increment it with omega t, 0, 45, 90, see which way the clock winds. It's either going to be left or right-hand polarization or linear if there's no phase difference. Do you all follow me? It's pretty straightforward. Last thing is, how could I make this elliptical polarization? If I wanted an ellipse rather than a straight, there's so many ways, but think of one. Anything. How about if I make this 2 E naught and that E naught? Wouldn't that create an ellipse rather than a circle? Sure, I could do it that way. Another way I could do it is instead of making that a 90-degree shift there, I could make it 45 and would trace an ellipse out with the tip of that thing. Do y'all follow me? So there's really a ton of ways to get polarization. Right hand, left hand, elliptical or circular, or linear. And it doesn't matter to me. The mathematics really aren't that important. What's important is to understand, send out a right hand circuit polarized, get back a left hand from any conducting object, and if you have elliptical polarization and you have the radar field and you rotate the radar until you get maximum return, that's probably the alignment of the velocity field that's reflecting, that's causing it to be reflected. And that's polarization in a nutshell. I don't go bananas here. The way Dr. Wentworth has several things in here about polarization, questions and things like that. It's not a big deal to me. Just understand what it is and why it's important. All right. Now we get transmission and reflection from surfaces or interfaces. This one's important, so I'm going to start fresh. By the way, if you're wondering about, can anybody think of a polarization filter? Just think for a second.
Sunglasses.
Polarized sunglasses, exactly. Have you ever taken 2 pair of polarized, does anybody have some polarized sunglasses here? You have them? Anybody else have a pair? You got them here?
Not with me.
Does anybody have a pair of polarized sunglasses besides him? Because if you take a pair of polarized sunglasses, the things you'll find, that's a polarization filter. They have very thin, long slits, and light polarized, and the direction of the slits will propagate right through. Well, basically right through. You still get a tint. But any light that's polarized perpendicular to that won't get through at all. So if you take 2 polarized lenses and you start rotating, you'll see through them perfectly, and then it'll go absolutely black when they're at 90 degrees to each other. When one slits this way and the other slits that way. Has anybody ever tried that? I wish we had 2 pairs. It's not a sunny day. But it's a neat, that's the best, simplest polarization filter that I can think of, I can show you. But in electromagnetics, we have polarization filters that'll actually get rid of any right or left circular polarized waves, as well as just eliminating certain types of linear polarizations, and that's pretty cool. Okay. Now, this is reflection from surfaces. So write this down. And this is called normal incidence. Normal or perpendicular incidence. So what do I mean by that? All right, we're talking about plane wave propagation, and we're going to have 2 surfaces. Here's the interface. And this is going to be region 1 on this side, and this is region 2. And now, this is going to be the z direction. And I'm going to stick with Dr. Wentworth's, this would be the x coordinate right here for x dimension. we're gonna have an electric field right here that's propagating in this direction, given by some E naught incident, e to the positive, or I'm sorry, negative, pardon me, minus j beta 1 z ax. And that field's coming in, and it's gonna strike that. It's coming this way. Then there's gonna be electric field. When this hits, there's electric field that's gonna actually be scattered back this way. That's the reflected field. And that's some E naught reflected, e to the positive j beta 1 z ax. Now remember, that minus j beta 1 z means it's propagating the positive z direction. The positive j beta 1 z means it's propagating in the negative direction. Y'all remember that from before? The two, if you have a negative value here, it's actually propagating the positive direction. And likewise, if you have a positive value for that coefficient, the exponential, then it's going in the negative direction. But you'll also have some that actually propagates through. So you're gonna have an electromagnetic field that actually propagates through or is transmitted. And E transmitted is E naught transmitted times e to the minus j beta 2 z in the ax direction. Now those are the electric field quantities, and I'm going to make this interface between these two regions be at z equals 0 to make things easier. In region 1, we have some beta 1, we have some eta 1, and in region 2, we have some beta 2 and some eta 2. And to be frank about it, in region 2, we could make it a lossy material very easily. Everything I'm about to show you holds true. So that's the electric field. By the same token, you're going to have a magnet. Anytime you have a propagating electric, you have a propagating magnetic. So we would have an incident magnetic field that would have a value of really E naught incident over eta 1, e to the minus j beta 1 z in the AY direction. And I'd have it H reflected, which would be E naught reflected over eta 1, but have a minus sign there because it's going the other direction. And it would be times E to the minus, or positive, pardon me, j beta 1 z in the AY direction. And then you would have a transmitted H field, which would be H naught transmitted, or really, call it E naught transmitted over eta 2, and it's times E to the minus j beta 2 times z in the AY direction. So, got incident reflected electric field, transmitted electric field, incident reflected magnetic field, transmitted magnetic field. Y'all remember that when I developed eta, intrinsic impedance, that's the ratio of E naught incident over H naught incident. Do y'all remember that class? And that is for positive traveling waves, but for E naught reflected over H naught reflected, it's actually minus eta. So there has to be that minus right there. So now, you know, at the interface of any two regions, there's a couple of things that for me make one, you remember, you have to know this stuff pretty well. The tangent values of the electric field on one side of the interface have to be equal to the tangent values on the other side. The E tan 1 has to be E tan 2. Do y'all remember that? That's very important. Same with the magnetic fields. If there are no surface currents right there, then the magnetic fields on one side, the tangent values on one side, have to be equal to the tangent value on the other side. How many remember that? E tan 1 is E tan 2, H tan 1 is H tan 2. This is very, very important. It's one of the foundational things that really allow us to do so much in electromagnetics. So the reason I chose that interface to be at z equals 0, it makes the math easy. You see, on this side, at any point Z, especially at Z equals 0, the incident field when Z is 0 is just E naught incident, right, in the AX direction. The reflected field is just E naught reflected. So let's take a look at here at Z equals 0. I have E naught incident plus E naught reflected is equal to E naught transmitted. That's pretty simple, right? The E to the J bit things go away. That's the reason you always choose the interface. The location makes it easiest to do the problem, which is at Z equals 0. Then when we take a look at the magnetic field, I have E naught incident over A to 1 minus E naught reflected over A to 1 is equal to E naught transmitted over A to 1, or A to 2, pardon me, A to 2. Do y'all follow me on this class? And there I just set Z equals 0. I take the magnetic field on this side. Here's with the demarcation line. All this is region 1, all that's region 2. And now I go ahead and I say H incident plus H reflected equal H transmitted. And it's at Z equals 0. Do y'all follow me? All right. Now, we're engineers, we always like to get things down to the shorthand notation, make them easy to understand and easy to solve problems with, right? So I come over here, I'm gonna replace E naught transmitted with this. So now I'm gonna have this be equal to E naught incident plus E naught reflected over A to 2 is equal to this. Now I have one equation with two unknowns, right? Y'all follow me? I got rid of the transmitted field. I just have reflected and incident. Y'all follow me? Okay. Now what I'm going to do is simply divide. I'm going to create a new constant. And this is the reflection coefficient. And the symbol is given as this, same as it was with transmission line theory. We define the reflection coefficient as the reflected field's magnitude, or E naught reflected, over E naught incident. So now I come over here, and I'm going to divide everything by E naught incident. Do y'all follow me? And when I do, I get what? I get 1 over A to 1 minus reflection coefficient over A to 1 is equal to 1 plus reflection coefficient over A to 2. Do y'all follow me? I'm just doing the division, and I've put in that reflection coefficient right there. That's the important symbol. Now I go ahead and I'm going to just move things around so I define the reflection coefficient in terms of A to 2 and A to 1. And you can do this a couple of ways. We could go ahead and multiply both sides by A to 1, A to 2, and I'd have A to 2 here, A to 2 here, A to 1 here, A to 1 here, and then collect terms. If you want to, I'll do it. But if you do it, you find it's what? A to 2 minus A to 1 over A to 2 plus A to 1. You can do that fairly straightforward. If you go ahead and just multiply by A to 2, A to 1, this becomes A to 2 here. This becomes A to 2 times that. This becomes A to 1 plus A to 1 times reflection coefficient. Then you gather the reflection coefficient terms, and you're going to have A to 2 plus A to 1. Reflection coefficient is equal to A to 2 minus A to 1, and from there it's pretty obvious. You just divide by A to 2, A to 1, and you have what I put there. This is called reflection coefficient, and again, it's equal to the value of E naught reflected over E naught incident. Now, there's also a transmission coefficient. Transmission coefficient is equal to 1 plus the reflection coefficient, and that's the ratio of the transmitted electric field to the incident electric field. Y'all follow me on this? I could go ahead and just start here, and then instead of solving for, or I could go ahead and say that E naught reflected was E naught transmitted plus or minus E naught incident, and I can replace these two and get everything in terms of E naught transmitted and E naught incident. But it will come down to this value, and this itself will be equal to 2 times eta 2 over eta 1 plus eta 2. This is always the way it's going to be, and this is the transmission coefficient right there, reflection transmission. So, now, the problem portion of this thing. Best way to do this is with a few examples. Let's take a look at it. So, if I have media, and I'm going to assume that this is air, and this is, say, epsilon relative is equal to 9, U relative is equal to 1, and sigma is 0. I've got an electric field propagating in this direction, and I say that's 10 volts per meter amplitude. It's coming in, it's normally incident on this region. And I simply want to know what the transmitted field's magnitude is. I just want to know the magnitude. How would you get that? Take a look at it for a second. Well, obviously the one thing we need is what? The intrinsic impedances. Do you agree with that, class? Gotta have that. So what's the intrinsic impedance of free space or air? 120 pi ohms, right? What is it over here? How do I get it? I would say the intrinsic impedance of region 2 would be equal to square root of what? Normally it's j omega mu over sigma plus j omega epsilon, but since sigma is 0, it's the square root of mu over epsilon, right? Y'all agree with that? All right, what's that gonna be? Well, that's the square root of mu naught over epsilon naught times square root of mu relative over epsilon relative. Square root of mu naught over epsilon naught is 125. And mu relative is 1, epsilon relative is 9, so it's divided by square root of 9 is 3. So this is 40 pi, correct, class? Again, I'm just turning the crank on the numbers. Okay. So, now look, we can get the reflection coefficient first, and then add 1 to it, and we'd have the transmission coefficient. Doesn't matter, right? Why don't we go ahead and get the reflection coefficient, since we're interested in that. It would be eta 2, right? Minus eta 1 over eta 2 plus eta 1, right? Equal, take a look at this. Eta 2 is 40 pi, right? Minus eta 1 is 120 pi, over the sum of those is 160 pi, correct, class? All right, what's that gonna be? Well, it's 4 minus 12, right? Over, it's going to be minus 8 over 16, or minus 1/2. Is that right? All right. What, by looking at this, is the transmission coefficient? 1 plus reflection coefficient, or 1/2. Do you agree with that? Right. It has to be, correct. Just add 1 plus minus 1/2 is plus 1/2, correct, class? All right. So therefore, what's the magnitude of the transmitted field? What's E transmitted? 1/2 times 10 volts, isn't it, class? Right. So it would be 1/2 times 10 volts, or it's equal to 5 volts per meter. What's the reflected field? Minus 1/2 times 10, or magnitude would be, or I should say the coefficient would be minus 5 volts per meter. Correct, class? Now, this is where people go wrong. We're in a hurry. They look at this and they say, well, half the power went through, half the power reflected. That's wrong. Because what is power? We take a look at the transmitted power and erase this. What is it going to be? Think about what we just did earlier. I'll help you out here. When you talk about power, if it's lossless, always remember that average power flow, if it's lossless, is 1/2, and its magnitude of the E field squared over the magnitude of eta. Now this is for a lossless region. There's no cosine, there's no e to the minus 2 alpha z in this case. This is a lossless region. So if we take a look at the transmitted power, P transmitted, this is power density really, it would be 1/2 magnitude of the field transmitted. Well, that's 5 volts per meter, but it's squared, right? Divided by 82. 82 is 45, right? That would be watts per meter squared, and it would be going in the positive AZ direction. P reflected, on the other hand, this is average power density reflected, would be 1/2 times minus 5 squared, but not over 40, but over 120 pi, right? And that would be going in the negative or minus AZ direction. And you can see these are not equal because 8 is different. That's the reason. The intrinsic impedance in region 2 is much less than in region 1, even though the magnitude of the fields, the electric fields, are the same. Do you all see that, class? Okay? Good with it? So, if I have the electric field transmitted, what's the magnitude of the magnetic field transmitted? What is this value? What do you know the ratio of E to H is? Say again?
You just divide by eta.
The ratio of E to H is eta, right? So that means if you have the E field, you want the H field, you simply say you take the E field transmitted and divided it by eta 2, and you would have the H field. Do you see how straightforward this is? And same thing if you wanted the H field in reflected H field, okay? So just remember those things and we'll get along fine. Now, these are for, so far, this has to do with normal incidence, and I didn't make it very complicated. I want to tell you one other thing. This doesn't have to be a lossless region, region 2. This could have a value of sigma that is significant, and you would still use that equation for transmission coefficient and this equation for reflection coefficient, but then you would get complex values for both of them if it's lossy. Do y'all follow me on that? And you got to be aware of that. I'll give you problems that deal with these things, but I want to make sure that I stress the fact that in region 2, it could be lossy. And there could be other factors. I may want to know how far into region 2. First, I might not want to know the power density just inside region 2 at Z equals 0 just on the other side, power density. And I want to know where the power density drops to only 10% of the surface power density. So that would mean E to the minus 2 alpha Z would be equal to, say, 0.1 or something, where, say if it's 10%, 0.1, and then I'd have to figure out what that value of Z was. Do y'all follow me, class? So there are different types of questions can be asked about this. You have to be aware of what's really going on. Now, we'll cover reflection at, and transmission at oblique incidences, and that's kind of an interesting topic in and of itself. I'm going to say one other thing about this now. The quiz will be on Friday. Monday is Memorial Day, right? We have Monday off. So, we'll get your quizzes back on Wednesday. Yeah.
And that quiz will be from the stuff we covered from Wednesday to.
It's everything. It's always, but everything builds. You can't really understand the last bit of material if you don't understand the first. And, so it's one of those things you have to keep up and have to stay tuned to what's going on. I'm going to say one thing. Yeah, if you are looking ahead and you look at oblique polarization and you're thinking, oh, these are complicated equations, I would give you equations for transmission and reflection for oblique. I'm not going to require you to memorize those because they're a little more tedious. But all this other stuff we're covering, this has to be committed. You have to know this from memory, and the way you do it is do the homework when it's assigned. Always spend a couple hours at least between every class period doing that homework, and keep up with it and ask questions if you don't understand something. And don't get too casual, because it's summertime, you can absolutely get clobbered because it covers so much. It's covering things much, much faster. It's more of them, so you can get lost and fail in a hurry. I don't want that in this class. I want to make sure everybody keeps up, and I try to encourage you. But look, we're missing a lot of kids. According to my roster, I think, I'm not sure if we started with 24 or whatever, but now I don't even know what's that. How many guys? 2, 4, 6, 8, 10, 12, 13. It may have been reduced. I thought we started that high, but I could be wrong. That was what?
So we've never had 24 in here.
We've had 24 enrolled at one time. Not here, but I mean.
I thought this was the rules last size.
I can't tell you how many people missed the first day of my other class. I thought it was canceled or something. Myself, who else? As a kid, is anybody else in my probability course in here? There's 2 of them in here that are my probability. They're not here.
Oh.